Welcome to The Explainer. Today, we're diving into drag and lift. Now, these are the invisible forces that pretty much govern everything, from how a curveball, curves, to how a massive jet gets off the ground. It's this constant battle, really, between resistance and flight, and it shapes our world in ways we don't even notice.
I mean, come on, you've done this, right? You stick your hand out the window of a moving car. You tilt it up, your hand just soars. You angle it down, it dives. You hold it flat, and it feels like the air is this thick, invisible wall pushing you back. That feeling? That's not just wind. That's pure physics in action.
And that simple push that you feel with your hand, that is the exact same force that engineers and designers are absolutely obsessed with. It's the force that supercars are shaped to cheat, and the very same force that parachutes are designed to catch. It has a name. It's called drag, and it's the first half of our story today.
Okay, so let's actually break that feeling down. Anytime an object moves through a fluid, and remember, air is a fluid, just like water, the fluid pushes back on it. And we can split that total push into two absolutely critical parts: drag and lift.
So let's go right back to your hand out the car window. That force shoving your hand towards the back of the car, that's your drag. But the force that pushes your hand up or down when you angle it, that's lift. So drag always fights against the motion, while lift acts at a right angle to it. It's that simple.
Okay, but here's where it gets really interesting. Drag isn't just one single thing. Nope. It's actually a team effort, a combination of two totally different kinds of resistance. And if you want to know how to beat drag, you got to know who you're up against.
So you've got two kinds. First, there's friction drag. Just think of it like, friction. It's the air itself literally rubbing and dragging along the object's skin. The more skin, the more friction drag. The other one is pressure drag, and that's all about the object's shape. It's the high-pressure pileup of air on the front and the empty, low-pressure void it leaves in the back.
And just look at how much the orientation of an object changes everything. It's kind of wild. You take a flat plate, hold it parallel to the wind, almost all the drag you feel is from friction along its top and bottom. But turn that exact same plate 90 degrees so it's facing the wind like a stop sign. Now friction drag is basically zero. The drag is almost all pressure drag. Same object, totally different physics.
Okay, so if pressure drag is the big bad guy for, blunt objects, the solution seems obvious, right? Just make the shape better. And that, right there, is the whole idea behind streamlining.
But there's always a catch, isn't there? When you take that blunt object and you stretch it out into this really sleek, streamlined shape, yeah, you slash the pressure drag. That's awesome. But you've also made the object bigger, right? You've increased its total surface area, which means you've just cranked up the friction drag. So the whole game of streamlining is finding that perfect balance to minimize the total drag, not just one type.
Okay, so pop quiz time. Based on everything we've just talked about, this should be a piece of cake. To reduce the drag on a ball, you'd want to make its surface as absolutely smooth as possible, right? I mean, less friction, less drag. Seems logical.
Yeah, no, completely wrong. And this is one of the coolest, most counterintuitive things in all of aerodynamics. Just look at this. At the right speed, a rough sphere has way less drag than a perfectly smooth one. Its drag coefficient just tanks from 0.5 all the way down to 0.1. It's so weird and dramatic that scientists call it the drag crisis.
So what in the world is happening here? Well, those little dimples on a golf ball do something amazing. They create this tiny, thin layer of chaotic, turbulent air right on the ball's surface. Now, this turbulent layer has more energy than a smooth, laminar flow. And that extra energy lets the air stick to the back of the ball just a little bit longer before it peels off. This makes the low-pressure wake behind the ball much smaller, and a smaller wake means way less pressure drag.
Let that sink in. A 5 times reduction in drag. That one, totally backward-sounding trick is the entire reason a dimpled golf ball flies so much farther than a smooth one would. It's an incredible piece of engineering.
All right, so we've spent a lot of time talking about how to fight drag, how to reduce it. But what about the other half of the story?
How do we flip the script and use these same principles to create a force, to create lift, and get something ridiculously heavy, like an airplane, up into the sky?
It really all comes down to the shape of the wing, which is called an airfoil. It's genius, really. It's shaped specifically to make the air going over the curved top have to travel a longer path, and therefore travel faster than the air taking the shortcut along the flatter bottom. And a rule in physics called Bernoulli's principle says that faster-moving air has lower pressure. So now you have high pressure underneath the wing, low pressure on top of it, and that difference creates a net upward push. That's lift.
Now, a pilot can get even more lift just by pitching the nose of the plane up. This increases what's called the wing's angle of attack. And as that angle gets steeper, the lift gets stronger, but only up to a point. If you go too far, usually around 15 or 16 degrees, something really dangerous happens.
And that's what pilots call a stall. If you get that angle too high, the air just can't stick to the top of the wing anymore. It separates, creating this big, messy, turbulent wake. The pressure difference that was creating all that lift just collapses, and the wing effectively stops flying. It's a critical situation that pilots train endlessly to avoid and to recover from.
So, if there's this hard limit on the angle of attack, how in the world do you get enough lift to take off or land, especially at low speeds? Well, engineers and even athletes have found some really clever ways to kind of hack the system.
Take a look at this. When an airplane deploys what are called double-slotted flaps, the wing's maximum lift coefficient can more than double. It goes from about 1.5 up to almost 3.5. That's huge. But look at the other side of the equation. The drag goes through the roof. We're talking a 5-fold increase. And you know what? That trade-off is totally worth it. Because you only need that insane amount of lift for very short periods, right, during takeoff and landing. It allows massive planes to use shorter runways and fly at much safer, slower speeds. As soon as they're up at cruising altitude, the flaps get tucked away to minimize drag and save a ton of fuel.
But wings and flaps aren't the only way to get lift. You can also do it with spin, and this is called the Magnus effect. When a ball is spinning, its surface actually drags a thin layer of air around with it. On one side, that layer of air is moving with the main airflow, speeding it up. On the other side, it's moving against the airflow, slowing it down. And just like on a wing, that difference in speed creates a pressure difference, which creates lift.
And once you know about it, you see this everywhere in sports. That backspin on a tennis ball or a golf ball, that's the Magnus effect, giving it extra lift, letting it just hang in the air for longer. And a pitcher's curveball? That's not some kind of magic trick. It's the Magnus effect, creating a powerful sideways lift that makes the ball literally curve through the air. And really, these are the very principles that took flight from being just a crazy dream to a hard engineering science. You know, the Wright brothers, they weren't just brave tinkerers. They were serious researchers. They built their own wind tunnel and they methodically studied these exact forces, creating the scientific foundation that lets us design the incredible aircraft we have today.
So, the next time you do stick your hand out of a car window, or you watch a pitcher throw a wicked curveball, or you see a giant jetliner climbing into the clouds, you'll know what's really going on. You'll see that beautiful, invisible dance between drag and lift, the forces that quite literally move our world. Thanks for joining us for The Explainer.